Sup, Calc 3, pop that color! 13.2, derivatives and integrals. Oh man, terms we're familiar with. And we're going to relate those with our vector functions. All right, objective 6. Objective 6 is define the derivative of a vector valued function. All right, let's kind of make sense of all this stuff. Let's say we have some vector function r of t. Here's our notation. Things we should be really, really familiar with. That, remember, is our OG. Remember when we used to have to do the derivative using the OG and it would take forever and it would be no fun? We're not going to make you do that anymore. But let's say we have some function r of t and it's some curve. Okay, we have some curve. And let's say we are going to define spling, right? Let's say that's r1 of t. Okay, that's that vector. And then remember, let's say we have some other vector. Let's go with this dude way over spling, that guy right there. We'll make that r of, we'll just go t plus h. So we're adding some distance h to it. If we were to connect those two, that would be the secant line. Remember that? That'd be the secant line. Be a secant vector in 3 space. Okay, or in 2 space, we could still represent these as vectors when we have the i's, the j's, the k's, and the t's associated to it. Now, remember, if we take that h, that average rate of change, and we shrink it, we shrink, and we get closer and closer and closer to, let's say, this vector right here, or that point right there. As I shrink it, the average rate of change becomes an instantaneous rate of change. Remember, the instantaneous rate of change is our tangent vector. So that's what we're after here. We're going to find derivatives that are going to allow us to find things instantaneously, vectors instantaneously. So as we're going around this curve in space, we can know what's happening instantaneously. Okay, so that's what we're kind of after right here. Okay, theorem. If r of t is made up of 3 components, x equals f of t, y equals g of t, and z equals h of t, then the derivative of that is simply the derivative of each one of those components. Just each one. Now there's a cool proof that goes with this, but I thought it'd be a lot more fun to see if you guys could kind of create and learn how to do proofs in class. So remind me, that's the first thing we should be doing next class period. Okay, example 1. Plus we don't want this derivative to go on forever. Now hit pause, and see if you can get this next one on your own. After all, it just says find the derivative. Right, didn't we just say it's just each one of the components? All right, so I'm going to write r of t in component form. Let's go, that'd be t to the negative 1. Remember, we like to write things with negative and rational exponents. So that's what we get here. I'm going to put pi of t in parentheses. And then just to find the derivative, right, let's check our derivative skills, see what we remember from Calc BC. That'd be negative t to the negative 2. That would be e to the 2t. That change. So we got that 2 out in front. And then this guy here would be positive 2 sine of pi over 2, but that pi over 2 change, and the derivative of pi t is pi. Booyah, that is it. Easy peasy, chop on easy. R prime of t refers to what we call the in 3 space, 2 space, but when we write it in vector form as the tangent vector, and the tangent line is the line through P that is also parallel to your tangent vector. We also have a unit vector. Unit vector goes hand in hand with our unit tangent vector goes hand in hand with our unit vector that we did earlier, and that is simply r prime of t over the magnitude of r prime of t. Okay, remember we did that before. So if I said to find the unit tangent vector for our example 1 up here, it is simply our unit tangent vector at t equals 1 is equal to the derivative of r at 1 over that dude's magnitude. Okay, so if we were to put a 1 into all of those bad boys, I would get the vector negative 1, 2e squared, and 0, because sine of pi is 0, all over the magnitude of that, which would be the square root of negative 1 squared, plus the square root of that squared, which would be 4e to the 4th. And we could split it up, negative 1 over it, 2e squared over it, and 0 over it, if we wanted to write it a little bit fancier. Okay? All right, next up, example 2. What's this say? It says, we're going to sketch, we have a curve in 3 space, 2 space it looks like. We could draw it in 2 space because we don't have a k component, z component. r of t, and we're going to find r prime of t, sketch r of 1 and r prime of 1. Okay. All right, let's do it. Let's do it. Well, can I sketch r of t? Let's see. Remember to do that, we do a little table, splang. Let's just go 0, 1, and 2. You pick any values you want here to graph it, right? But we want to pick numbers that would be easy to work with. Plug a 0 in there, you get 0, and you get ichiban, lies, niban, 0, 0, 2, so spling. So we get that guy there. Plug a 1 in there, I get an ichiban and an ichiban. Get gaze. And then plug a 2 in there, and I get this square root of 2. Maybe I should have chose something better like fout. But 2 in there, and I get 0. So that'd be about 1.4. Boom. So that's what the vector is kind of looking like, going in that direction there. All right, they asked me to sketch R1. Okay, well, R1, let's see here. R1 would be equal to, let's plug it in there, and I'm going to just write it in component form. That'd be 1, 1. Yes. Boom. That's it. So that'd be that vector right there. Booyah. That's what R1 would be. Okay. Remember, that's the vector is the combination of all those terminals, right? That's what that would be. So that's drawing R1. And then they also want me to sketch, find R prime of t and sketch R prime of 1. R prime of t would just be the derivative of that, which would be 1/2 t to the negative 1/2, comma, that'd just be -1. Boom. That right there. So R prime of 1 would be equal to 1/2, comma, -1. Okay, you know what's interesting about that is if I were to draw that, that right there would be the derivative, but if I were to draw that, that'd be 1/2 down 1, so that'd be this guy. Okay, now, any equivalent, remember, a vector is a magnitude and a direction that are all equivalent to each other. So believe it or not, the tangent at this value, boom, is equivalent. Those two are equivalent to each other. So it actually doesn't matter how you draw it. You could draw it anywhere in my 2 space, as long as it has the same magnitude and same direction, they're equal to each other. But this would be R prime of 1, okay, and this would be R prime of 1 in relationship to our vector R of t, okay, that would be the tangent vector, okay? All right, let's keep rolling. Example 3, we want to find the parametric equations of the tangent line to the helix. Remember, it's a helix if it has an x component, that's cosine or sine, a y component, that's cosine and sine, and then a z component of something else. That's not one of those trig functions. Okay, and then you get a helix. Now, this would be going up the z axis. Okay, and we want to find the parametric equations at the point 0, 1, and pi over 2. Okay, and for the tangent line. Okay. So tangent line means derivative, right? So let's write this first. This would be 2 cosine of t. I find it helpful to always writing these in component form, because then when I want to find the derivative or the tangent line, which means I got to find the derivative of all these, kind of real easy to do, right? It's like you have 3 mini problems, and if I have it in component form, it's kind of a little bit easier to see. Okay. Now the question is, when you're doing these, you kind of have to determine, well, what the heck is t? Okay. So the main question here is, what is t, right? And we can pick t to work out for what we need it to for the problem, and we're trying to find this at the point 0, 1, and pi over 2. So let's think about this a little bit. Okay, I know I already took the derivative, but if I want to know what is t, and here's my point, okay, then that means I'm going to set 0 equal to 2 cosine of t, because that's what the x is. We're going to set 1 equal to sine of t, because that's what the y is, or the j component. And last but not least, we're going to set pi over 2 equal to t. Well, booyah! That means t is pi over 2. Makes sense, right? So let's go ahead and find r prime of pi over 2, right? Just plug a pi over 2 into all those bad boys. You get -2, 0, and 1. That would be the tangent vector And I know I don't know if it really said it, but that would be the tangent vector at t equals pi over 2. All right, now remember, one of the things we needed to do here is we needed to find the parametric equations. In order to find the parametric equations, right, just like, almost like finding the equation of a tangent line back in the day, we needed a point and the slope. Okay, and kind of what we need here is we kind of need a point and the slope. Well, we kind of got the slope right there, correct? Negative 2, 0, 1, and we need a point. Well, shoot, we already got a point. So in order to find the parametric equations, it'd be nice to have the vector equation, right, for that guy up there. And the vector equation for that guy would be your point, 0, 1, pi over 2. And we did this earlier this year, plus t times your slope, negative 2, 0, 1. Right, kind of like going back in the day and doing these equation of a line problems. We just need a point and a slope. Actually, maybe a little bit easier than what we did in BC when we did a little y minus y1 equals m times the quantity x minus x1. But this would simply be x. Ooh, let me just already write it. Yeah, I'm already gonna. I mean, that's already, you know, equivalent to the vector equation. But they asked me earlier to write the parametric equations, which would be x equals 0. Minus 2t. It'd be y equals, what would that be? 1. It'd just be Ichiban. And then z would be equal to pi over 2 plus t. Boom. There are your parametric equations. Okay? All right, let's keep rolling. 6, we've got all of these rules, you guys. They can be a little bit annoying. They are pretty much, they are very, I feel like, self-explanatory. The one thing you have to understand is number 5. When you do the cross product, order matters. Okay, and we learned last unit in chapter 12 that order matters, because if not, if we flip it, then we'll get the opposite, right? We'll get the negative of it. Okay, so you've got to be careful. If you remember, we did that last unit. 6 is kind of like a chain rule. And ordering these things matter. So make sure you look at these, the dot product. You know, we have a dot product one up there. Number 4 is a dot product, right? 3 is kind of like a product rule like we did back in the day. 4 is a dot product, where 3 and 4, the order doesn't necessarily matter, but 5 does. And since 5 does, I try to do them, like all of these formulas are kind of the same. You know, just keep them in that order so that you don't make a mistake when you need to when you're doing the cross product, okay? If R of t and if R of t is differentiable and the magnitude is constant, and R of t dot R prime of t is equal to 0. What does that mean? Say it, say it, say it. It begins with a O. It is orthogonal. Okay? Is that all the notes we got here? Yeah, because we're just going to do a little bit of practice. Okay. Or no. I'm giving you 2 vectors, R1 and R2, and we want to find the acute angle between those. Now, when you think of finding the angle between those, you should immediately think of our formula that we used earlier in chapter 12, which is cosine of theta is equal to R1 prime of t dot R2 prime of t all over R1 prime of t, that magnitude, times the magnitude of 2. Remember, we used this formula in chapter 2. But the interesting thing here is that we have to make sure we have a time to work with, because if we don't have a time to work with, we're not going to be able to get something that we could find the angle of. So we are going to start this at the origin, okay, at the origin. And if we're at the origin, then R1 of t would be, what would make it 0, 0, 0. And when I ask it, I'm saying what time? You know, what would t have to be to make it 0, 0, 0? Well, if you look up here, if t was 0, all of those would be 0. So that means t equals 1 for that first vector function. Okay, what about my second vector function? What would t have to be for it to be 0, 0, 0? It's not always time equals 0, which is kind of strange, kind of different, kind of weird, right? And it looks here, if t were 1, it would be equal to 0, comma 0, comma 0. And remember, the reason why I need this, and I need to know, what vectors I'm dealing with and what time I'm dealing with them, is because it says right here that we want to find the acute angle at the origin. In order to find it at the origin, I need to know what vectors we're talking about. And in order to know what vectors I'm talking about, I need to know what time we're talking about. Okay, so now what I would like you to do is hit pause and see if you can get all of this on your own. All right, cosine of theta is equal to, okay, I'm going to come over here, maybe use a different color, and I am going to need to know what r prime of t is. Okay, ooh, shoot, I kind of ran out of space. Oh, inverse tangent. Do you guys remember? That's 1 over 1 plus t squared. Sine of t would be cosine of t, and I'm running out of space, but that'd be 2t. So then r prime of 1, which would go right here, or r prime of, ooh, shame on me. This would be 0, we said, right? Right? Because 0, 0, 0 gives me 0, 0, 0. Okay. Now, if I plug a 0 into all of those guys, because it would be r prime, right? We needed to know what time it was. It would be 1, 1, 0. Okay, so that'd be 1, 1, 0. Okay, and then I got to dot that. Let's find the derivative of my second vector function, which would be 2t minus 1, 2, and 1 over t. But we're going to do that at 1, which would be 1, comma 2, comma ichiban. Right? Yes. And that's all over the magnitude of this first guy, right? The magnitude, that's my formula right there, which would be the square root of 1 squared plus 1 squared, which is 2, times this one, the magnitude of that guy at t equals 1, which would be 1 squared plus 2 squared plus 1 squared would be 6. Okay? I think you can do this one without a calculator. Dot product would be 1 times 1 plus 1 times 2 plus 0 times would be 0. Okay, so I would get 3 over the square root of 12, right? 3 over the square root of 12. Square root of 12 is 2 radical 3. Radical 3, radical 3, spling, spling. That would be radical 3 over 2. If I simplify it, and cosine of theta is equal to radical 3 over 2 at theta equals pi over 6, or 30 degrees. That was some work. That was some work. Boy, we're going to have to practice that in class. Remember, trying to keep this video short, that problem took a while, so let's roll. Let's roll. All right. This next one, we're looking at some of these guys. Okay, probably should have did these notes a little bit better. Okay, and it's just showing that dot product, you can do it directly or you can use the formulas. Okay, how do you do it directly? Directly is, please excuse my dear Aunt Sally. Well, please excuse my dear Aunt Sally always tells me to do the parentheses first. So let's dot my R1 with my R2, 0, 0, t to the fourth, and then let's take the derivative of it, right? This would be doing it directly. What would that be? That'd be 0, 0, and then t to the 7th. And then the derivative of that would be 7t to the 6th. Boom! Yeah, donezo. Okay, how do we do it indirectly? Well, you would do it indirectly by using the formula. Let's go spling, spling. Let's go a little screen shotty shot. Booyah. It's kind of like the product rule, right? Shoot. I might want to erase what I got there, so I will. But let's go ahead and do it using the rule. And the rule says you can do it kind of like by doing a product rule of this stuff, which it would be the first guy derivative, which would be, I'm going to just write it in, what would they be, 2, yell at me if I make a boo, 3t squared, and I'm going to dot that with this guy, which would be 0, 0, t to the 4th. And I'm going to add that to the OG of the first one, 2t, 3t squared plus, comma, t to the 3rd. And I'm going to dot that with the derivative of this, which would be 0, 0, 4t cubed. All right, so let's do a whole bunch of dotty dots. Okay, if you dot that, you get 3t to the 6 plus, if you dot this 0, 0, and that would be 4t to the 6. Oh, 7t to the 6. I got the same answer. That's what you're supposed to get. That's why they're equal to each other. All right. Can you please challenge yourself? Can you guys please do the next one on your own, like hit pause? We're just going to prove that the one for the cross product also works. It'd be awesome if you tried it on your own. I just think you will learn more. Okay, if you do, let's get rid of that bad boy. Oh, erase. What the? Whoa. All right. So now let's do it directly. Okay, let's do the cross product directly. Okay, so that means we're going to crossy cross. Okay, I, J, K. You know what? That's what you have to do for part of your homework. You have to prove that you get the same answer doing it using the formula. Okay? All right, let's see. Let's do it. Let's cover up the I. And if I cover this guy up, then it would be that would be, well, I'll write it chevron-ish. That would be 3t to the 6, right? Comma. All right, let's cover up that, and it would be negative, right, because it's opposite, and that would be 2t to the 5th. Yes, yes? And then the last but not least, cover up that, and you get zeros, right, because you get the zeros. Now let's take the derivative of that. And remember, when you do a cross product, you always get a vector as your answer. That gives me 18t to the 5th, and that gives me negative 10t to the 4th, and that gives me 0. And guess what? If you do the same thing, and what do I mean by the same thing? I'll go back here and do it, and then your job is to do it. Okay, maybe I'll check next class, and if you don't have it done, that's part of our pop quiz. Remember, order matters when we do the cross product one of these guys. Okay, so if you were to go Spling, and you were to use this guy, okay, and that's order does matter. You do the dot product of U prime or R1 prime with R2 plus R1 crossed with, no, I said dot, I think. U prime, R1 crossed with R2, and then R1 crossed with R prime of 2. Okay, and if you do that, guess what? Gonna get the same answer. Okay? All right, let's get to some integrals. And guess what? Just like derivatives, you know, if I ask you for R prime of t, then you just take the derivative of each one of those components. If I ask you for the antiderivative, then you just simply take the integral or the antiderivative of each one of the components. That's it. That's it. So let's get to work. Hit pause, see if you can get this one on your own. Okay? So if they ask me to find the integral from 0 to 1 of r of t dt, that is simply equal to the integral from 0 to 1 of t squared dt, and we'll call that I, plus the integral from 0 to 1 of e to the t dtj, and then it would be plus the integral from 0 to 1, gosh darn it, I'm running out of space, of negative 2 cosine pi t dt k. All right, so let's just take the antiderivative of each one of these, slap an ijk on it. That's all it really is doing. So that'd be 1/3 t to the 3rd from 0 to 1 I. Okay, plus that'd be e to the t from 0 to 1 plus j plus this would be, what would that antiderivative be? I think I need to look at that a little bit better. That would be a little bit of a antiderivative of negative cosine. That would be sine, and then it's going to have to do a little u sub. So that'd be 2 over pi sine of pi t from 0 to 1. Okay? All right, let's plug this stuff in. Plug a 1 and plug a 0 in. You're just going to get 1/3 I. Plus, plug a 1 and plug a 0 in. I am going to get e minus 1 j. Last but not least, plug a 1 in, I get sine of pi 0, plug a 0 in, sine of 0, 0, no k. Booyah, problem done. Whew, not bad, not bad, not bad. Ooh, what's different between this one and the other one? The other one, remember, we called that a defined definite integral. This is called an indefinite integral. Okay, so if I were to take the antiderivative of this, right, you just do each one separately. It'd be t squared I plus t cubed j, but what do I got to add? Since it's an indefinite integral, there's going to be some vector c, right, that constant. And remember, when we did these problems back in BC last one, just want to get this done. When we did this back in the day, and we gave you two pieces of information with an initial condition. I always told you the best way to do these problems is you define your vector function r of t, and that is equal to whatever they give you initially, okay, which is r of 1, okay, and then we're going to add to that. Remember we did this last year? And we would go from 1 to t, whatever value that is, right, from 1 to t of r prime of t dt. Okay, so then that means that would be equal to the vector 2, 5 plus the integral from 1 to t, and I'm going to just keep it like this. That'd be 3 comma 2t dt. Okay, and so remember, if you just solve this, it kind of works out for itself. Okay, we get that, and then what do we get plus? We get 3t comma t squared, and we're going to evaluate that. Well, let's go this from 1 to t, this from 1 to t. Okay, boom, and then remember, the c is going to take care of itself. Remember, there are multiple ways of doing this. If I plug the t in, what do I get? I get 3t minus 1. Okay, right? Did I get that right? 3t minus 3. 3t minus 3. I knew there was something wrong. And then if I plug that in there, I get t squared minus 1 for that guy, remember? Okay, and then I'm going to add these two vectors together, which would be 3t minus 1, and then t squared plus 4. Boom, and that's it. Shebang! There you go. That's a rappity-rap rap. That was really quick. We'll practice it like crazy in class, and let's make sure we're working hard in class. Aloha.